And also, I just wanted to make a brief point of clarification about the introduction. First, Helena, the pictures of Queen's University look quite different in the winter, so you might want to check those out as well. And secondly, well, our papers, I think, were part of the impetus for bar plots. I was actually not involved in that initiative at all, so the person who deserves the credit for that is Christina Bergman. Who I did talk about it with it on Twitter at the time, but yeah, credit for that goes entirely to her. Okay, so today I'm going to talk about how to identify and fix common problems with data visualization. Just give a quick overview of the topics that I'll discuss today. I think it's important when I start a talk to always emphasize why figures are so important when we're thinking about reproducible and transparent research practices. I'll spend quite a bit of time talking about bar graphs of continuous data, specifically why you shouldn't use them and what you should use instead to give readers more information about your data. And then I'll close with a few other common problems and how to identify and fix them. Okay, and just to clarify the philosophy for this session, I will be focusing more on the concepts of how to design a good visualization as opposed to the code of how to create these visualizations. For those of you who use R, I will give you a resource it's a flipbook that will help you to reproduce all of the graphs and the graph types that we create in the bar graphs portion. Using R. However, generally speaking, you can create graphs in a lot of different software packages, and so whatever you're comfortable with is the one you should use. But I think knowing how to make an effective graph is much more important at this phase. So, why figures? One of the reasons that I think it's really important to think about figures and data visualization when we are talking about rigor and reproducibility and transparent science is that data presentation is really the foundation of our collective scientific knowledge. So if we think about what happens when we look at a paper or we write a paper ourselves, you will all be aware that we often use figures to show the most important findings in our paper. So the take-home messages, the things that we really want authors to pay attention to, those things are typically highlighted in our figures. And we also know that the raw data underlying those figures aren't typically available. And that means that all that readers will ever know, both now and in the future, about our data set are based on the figures that we present. And so if we are systematically making poor choices about the types of figures that we're using, then we are depriving the scientific community of knowledge about the research that we conducted and the results of that research, not just now, but also in the future. And nobody wants to be responsible for ruining the future. So that's why I think it's really important to talk about data visualization. One of the other things that you'll notice throughout our presentation is that the research that I do typically focuses on fields that have small data sets, so sample sizes of often less than 10 or 15 independent observations per group, and sometimes as small as 3 to 6 independent observations per group. And you might be wondering why I focus on fields that typically use small data sets in the era of big data. So I'll just briefly address that. The first is that small data sets are very common in the basic biomedical and biological sciences, as well as in translational science. So for example, if we look at preclinical studies of cancer or stroke, the average sample size is 8 animals per group. These studies are also important because they influence decisions about what potential treatments advance to clinical trials or to future research. And the clinical trial process is very expensive, it's time consuming, it requires a lot of effort, and it exposes our patients to burdens and risks. So we want to make sure that the preclinical data and the information going into those trials is as strong as possible, so we're making the best choices that we can about what agents should really advance to clinical trials. And then the last thing is from the US perspective, when the National Institutes of Health, which is our major funder, are highlighting problems with reproducibility, they've been especially concerned with preclinical research, which again is often related to small sample sizes. Clinical trials have undergone a number of protections in recent decades, so practices like pre-registration, blinding, and randomization are more widely accepted and practiced, whereas those things are less likely to be used in small sample size studies. Okay, so what is the point of a visualization? What is an effective figure supposed to do? Well, there are four things that I'd ask you to keep in mind as we go through this presentation. The first is that an effective figure should immediately convey information about the study design. So from looking at your figure, I should be able to tell whether you're comparing independent groups, whether maybe you had a longitudinal study that looked at changes in individuals over time, or perhaps you had matched pairs of individuals who were related in some way. The next thing the figure should do is allow the readers to confirm that the statistical analysis is appropriate for the study design. So when I look at the statistical analysis plan, it should match up with what the study design characteristics are. The third thing is to illustrate important findings, and this is the one and only thing that most of us focus on when we're visualizing our data. So I think it's important to remember that illustrating important findings is only one of four things that a visualization needs to achieve. And the last thing that a visualization should do is allow the reader to critically evaluate the data. This is especially important for science, and it's the place where a lot of the visualizations, like the bar and line graphs that we regularly use in small sample size studies, run into problems. So I want to emphasize that my interest in improving data presentation comes from my own work. So I studied the pregnancy complication preeclampsia. And one of the things that we know about preeclampsia is while women tend to end up with a similar set of symptoms, they get there in very different ways. Some women have problems with the placenta, some women have problems with the fetus, other women have problems with maternal risk factors, and there are different pathophysiological pathways within each of these three things. And that means that for any biomarker we look at or any pathophysiological process, we expect it to be perfectly normal in some women with preeclampsia and very abnormal in others. So the field right now is really focused on how can we identify subgroups of patients who have particular pathophysiologies so that we can develop treatments for those pathophysiologies. And this is where my interest in bar graphs come from, because there are no subgroups in a bar graph. A bar graph is what we show when we want to mask heterogeneity. When we want to understand heterogeneity or differences in subgroups, then we need to use more informative visualizations. And so this is a problem that I was very concerned about and upset by. And I was in a conference sitting with a colleague of mine, and we were both frustrated because presentation after presentation was showing bar graphs, even though the session was about preeclampsia. And so I started thinking, okay, what can I do about this problem? And this led to this paper here. And which we published in PLOS Biology, which really looks in detail at the problems with using bar and line graphs to show continuous data. And this paper was viewed more than 100,000 times in the first month that it was published. It also contributed to policy changes in a number of journals. So journals such as PLOS Biology, eLife, and the Journal of Biological Chemistry. We also are aware that there are a number of editors and reviewers that use the paper when they're asking authors to improve their visualization during revision. And it was instrumental, I think, in launching the Bar Plots Kickstarter campaign, which was done by Christina Bergman and her colleagues. So there were a few key findings from the systematic review component of the paper. We looked at more than 700 papers published in a 3-month period in the top 15 physiology journals, or 25% of physiology journals, because that's what jet lag and transatlantic flights are for. And we found that almost all papers were using bar and line graphs to present continuous data. So 86% of papers had a bar graph, 63% had a line graph. When it came to more informative visualizations like dot plots, box plots, and histograms, researchers weren't using those. So only 13% of papers had a dot plot, and 5 to 8% had a box plot or a histogram. And that means that we are using figures that generally make it very difficult to critically evaluate the data and see the data distribution. We also found that the sample sizes were quite small, in most cases less than 10 independent observations per group. That bar graphs, the error bars in the bar graphs, 78% of the time were showing the mean and the standard error. Only 16% were showing the standard deviation. Confidence intervals were very rare. And that means that the bar graphs are telling us about the precision of the mean and not the variability in the data or the overlap between groups. And then we also found that this practice was so strong that when we looked at papers that were using non-parametric analyses, more than half of papers analyzed data that they have, or showed data that they have analyzed non-parametrically as either a mean and standard error or mean and standard deviation. And this is a problem because authors often use a non-parametric analysis when either they know that the data aren't normally distributed, and so the mean and standard error or standard deviation are likely to be misleading, or the sample size is too small to determine the data distribution. So you might be wondering, we had a paper that generated quite a bit of attention and changed some journal policies, so have we solved the problem yet? Well, we went back and looked at this question in a slightly different field, and we did an assessment of all journals published in the top 25% of peripheral vascular disease journals in September of 2018. And unfortunately, we found that we were nowhere close to having solved the problem. So we observed that among papers that had any type of data figure, almost half of them had a bar graph of continuous data. And the second place type of figure was not even close to being almost half of papers. So that meant that bar graphs were not only the most common type of figure, but also the most common data visualization problem. And that's why we're going to talk about them in much more detail. So you might be wondering, if lots of people are using bar graphs, and maybe I use them as well, then what's the big deal here? If everyone's doing it, then why shouldn't I use a bar graph to present my continuous data? One of the reasons for this is that many different data distributions can lead to exactly the same bar graph, and the underlying data distribution may suggest different conditions or different conclusions from the summary statistics alone. And so here's an example where I have 4 different data sets that will give me the same bar graph. Now, the first thing you'll immediately notice about the dot plot is that the first thing I can see is that the sample sizes are all very small. So there's a lot of uncertainty in each of these different data sets, which might affect how much confidence I have in the conclusions. But if I look at the data in more detail, in the first group shown in B, the second group has slightly higher values than the first group. Maybe this is a difference that I'm interested in investigating further. In the second panel, that slightly higher value seems to be driven by an outlier. This might not be something I'm so interested in investigating. In the third panel, there's some suggestion that I have a cluster of higher observations and a cluster of lower observations within each group. So I would want more data to know whether this is really a bimodal distribution or just an artifact of having to have of the observations that I happen to draw from a small sample. And if there were a bimodal distribution, I would want to know if there's some other factor that's explaining that distribution. For example, that men have lower values than women. And if that's the case, then I would need to account for that variable in my analysis and in my study design. And then in the last case, I have unequal n. So the values for the second group are clustered at the slightly higher end of the range compared to the values for the first group. But it could just be because there are so few observations in that group and I've underestimated the variability. And finally, I can't distinguish between these scenarios based on p-values alone. So there's really no substitute for seeing the data. So you might be saying, okay, well, I understand distributions can be different, but what if I know that my data are normally distributed? Can I still use a bar graph then? And as you may have guessed, the answer is of course not. And there are 2 different reasons for this. The first is that the bar graph doesn't allow you to critically evaluate the continuous data, which is one of our 4 objectives for figures. And the second is that bar graphs arbitrarily assign importance to the height of the bar, rather than focusing on the amount of overlap between groups or how the variability in the means the difference between the means compares to the variability in the data. And they do that in part by distorting our perception of the range of observed values. So if I look at this graph here, I can see this distortion issue. So the first thing that happens is I typically end the y-axis for my bar graph just above the error bar for the highest group. And that means that I can end up excluding values from my graph that are actually present in my data set. And this is called the zone of invisibility. The second problem is that we often start our bar graphs with a value of 0. And we'll talk about this a little bit more later. But sometimes 0 is a biologically and physiologically meaningful value. And in other cases, it's really not a meaningful value at all. And so if 0 is not biologically or physiologically possible, and the values around it will never occur in your data set, then you can actually end up dedicating a large amount of your graph to the zone of irrelevance, where you will never have any actual values. And this is the other way that the bar graph can distort our perception of the range of observed values. So what do I want you to remember from this? Well, that our interpretation depends on what we see. When we see a bar graph, the reader becomes a passive observer. So I can see that maybe the second group looks a little bit higher than the other groups. There's some overlap. Maybe this is an inference I'm interested in. Maybe it isn't. But when I see the dot plot, I immediately notice that the sample sizes are very small. There's a lot of uncertainty in the data set. I might have an outlier in the third group. And the group with the highest values is also the one with the smallest sample size, which makes me perhaps even more uncertain about whether this really is a meaningful difference that I should study further. So all data presentation methods are a reflection of reality, and looking at your data in a bar graph or in a line graph is a little bit like looking at a reflection in a wavy pond. You hypothesize that as a result of your experiment, you were going to find a duck. And you look at your data in your bar graph and you say, "Ooh, that looks like a duck. I'm pretty happy." But the reflection is wavy, there's some distortion. And maybe it's a duck, but maybe it's actually just an oddly shaped potato. And no one wants to waste time and effort and money and resources following something that they thought was a duck, only to end up with an oddly shaped potato. So it's really important to select visualization methods that minimize distortion. So if we shouldn't be using bar graphs, then what should we use instead? Well, this figure is a lot and it's going to build over time. I'm just showing it to you to let you know that it's there if you're working with your own data sets and if you're trying to figure out what to use. There's a lot of detail in this figure that will be helpful to you, but I'm just going to highlight some key points. So when you're working with continuous data and you have a very small sample size, it's best to use a dot plot. You can use them with any distributions, and they can also be helpful for median sample size if you happen to like dot plots. As your sample size gets a little bit larger, then the summary statistics shown by a box plot or a violin plot become more useful. And so you can start to combine the dot plot with a box plot or a violin plot. At some point, you will have too many dots and they will just create a mess of your figure without adding any information. When you get to that point, you have enough data that you can just get rid of the dot plot and create the box plot or the violin plot by itself. One really important thing to remember about box plots is if your distribution happens to be bimodal, that won't be visible in a dot plot. So always avoid a box plot for bimodal data and use a violin plot instead. And then the last point is the bar graphs. The point is not that you should never use them. It's that you should restrict the use of them to what they're intended for, which is counts or proportions. So for example, 50% of this webinar, people in this webinar are awake right now, would be a good graph to show in a bar graph. And these are things where we can think of the bar as being literally filled with data. So the bar height shows the value of the count or proportion, and the higher the bar, the higher the count or proportion is. But we should never use bar graphs for continuous data. You should move them to your dead to me list for visualizing continuous data. Okay, so some people will say that they still prefer bar graphs because they convey a clear message, and sometimes it's hard to see what's going on with a dot plot. Well, the good news here is that you often don't have to choose. You can use something called de-emphasis, emphasis, and de-emphasis in order to convey a clear message while still seeing individual data points if you're working with a small data set. There are two steps for this. Your first step is to make all of your data points visible, and there's a series of strategies that you can go through to do this, but I'm going to highlight the last one because it's the most effective thing, and this is symmetric jittering. So we're going to add a little bit of noise on the x-axis in order to spread out the data points so they're not on top of each other and we can see all of them. And we're going to do that in a symmetric way so that our eye can naturally outline the shape of the data distribution. That's the best way to make sure that all of your points are visible. The next thing we're going to do is use emphasis and de-emphasis. So we make sure that we have adequate white space between our different groups. And we are going to emphasize the summary statistic here, a median line, by putting it in black and in the foreground, or we could put it in a color. And then we're going to de-emphasize the data points and the axes by putting them in gray and in the background. So when I look at this figure, my eye is going to go immediately to the thing that's emphasized, which is the median line, and it'll jump out at me that this value in the third group is a little bit higher than the values in the other groups. But then I can still go back and take a second look and get a sense of the number of data points, the size of the sample, and the data distributions of each variable. So another popular strategy that people are using right now is to add dot plots to their bar graph. And you might be wondering, how about I just do that? Are we all happy then? And unfortunately, the answer is still no. It's better than a bar graph, but I would always rather have a dot plot any day. And basically, it comes down to a dot plot is everything that you need and nothing that you don't. So if I look at the graph here, the dot plot clearly shows the medians as well as the values for each individual data point. And I can easily see the magnitude of the difference between groups as well as the amount of overlap. With a bar graph, our picture is a lot more cluttered. So often the first thing that we'll do is shade our bars. And when we shade our bars, it can make it harder to see the data points that are inside those bars. The next point is that the bars and the shading and the vertical lines are actually chart junk. So we have a solid shape here creating the illusion of certainty, but that shape isn't actually adding any information. The means are exactly the same, whether there is a bar there or not. So the bar doesn't matter. And furthermore, when I say it creates the illusion of certainty, that bar looks just as solid, whether I have 2 data points or 2,000 data points. And in reality, those two situations are vastly different in terms of how much confidence I would have in the data. A third problem that we have in some data sets when values around 0 aren't relevant is that we can have a zone of irrelevance that falsely alters our perception of the size of a difference. And then there's also a phenomenon called within the bar bias. And this is a perceptual phenomenon where our brain looks at the bar graphs and we incorrectly believe that the points are more likely to fall within the bar instead of above the bar. And so this is another thing that potentially distorts our perception of the range of observed values. Okay, so I've mentioned that if you have a medium sample size, you might want to combine your dot plot with a box plot or violin plot. How can we do that effectively? What most people often do when they're starting out with a medium sample size is to just show the box plot. And again, a dot plot can be really helpful here if your sample sizes are on the smaller end, because it gives people the chance to check the distribution in more detail as well. And the distribution is something we should be less confident in with smaller sample size data. The other thing that people will sometimes do is they'll put what's called a strip plot or an unjitter dot plot where we have lots of overlapping points and we can't tell what's going on. So how do we fix this? Well, 4 things. The first thing we can do is use symmetric jittering, just like we talked about with good practices for dot plots. We also want to apply that when we're making a combination of a dot plot with a box plot or a violin plot. The next thing I've done in this graph is I've made the width of the box plot proportional to n. And I've also added the sample size in the label for the x-axis. People are busy, no one has time to count your data points. Make it easy for them. And then the last thing is I have one group here with only 4 observations that is far too small to show a box plot. And so I've actually removed the box plot for that group. And then in the first figure, which I would use with a sample size like the one shown here, which is a little bit smaller, I have emphasized the median line by putting it in color, and also the dots by putting them in the foreground and in black. And then I've de-emphasized the box plots by putting it in gray and in background. And I can reverse this by emphasizing the box plot and de-emphasizing the dot plot if I had a larger sample size or if I wanted to focus people's attention more on the box plot. Okay, now we're going to start controversy and fights because this is an ongoing debate in data visualization. And I know not everyone will agree with this, but here's my perspective on it. And this is the issue of, doesn't the y-axis always need to start at 0? So when I show this figure, I will sometimes get questions about this because this particular panel does involve a cut axis. Okay, so it's important to remember that data visualization and graph types are often designed for certain types of data. And the guidelines that go with that type of graph are also often designed for that same type of data. And so when we take a graph type and we move it over to a type of data that that it was never intended for, and then we bring all of the rules and guidelines along with it, very weird stuff happens. And this is an example of that. So I mentioned earlier that bar graphs are really designed for counts of proportions. So when you have a count or a proportion, then 0 is the true minimum value, right? You can't have a count or a percentage of less than 0. And the bar height is actually meaningful because the higher the bar is, the higher the count or the proportion. And so it makes sense to start our y-axis at 0. When we don't do that, then it changes our perception of the count or the proportion. So for example, here the y-axis starts at 80. So the true proportion shown by the first bar is 90%, but my eye sees 50% because the axis is cut. And this is potentially misleading and a problem. What happens when we attempt to apply the same rule when we're using bar graphs to visualize continuous data? Well, first of all, the bar height is arbitrary because 0 may not actually be the minimum value. And in many cases, 0 is not biologically possible. So let's take a look at 3 different scenarios. So in the first scenario, I have 2 different groups. The values are relatively close to 0. The zone of irrelevance is small. I can see the data clearly, and there are no problems. So starting my axis at 0 here makes sense, and it isn't a problem. When I look at the next graph, then I have a huge zone of irrelevance, and I have all my data points crammed into this tiny little space at the top of the graph. Now, remember, the goal of the graph is to help me examine how the difference in means compares to the variability in the data or the distributions and the amount of overlap between groups. And I can't see that information here because the data are all crammed into this very top segment of the graph. And so here we have a problem. And then in the last scenario, 0 is not the true minimum. So we actually have negative values. And I don't think there's anyone here that would argue that we should start the graph at 0 and just pretend the negative data doesn't exist. That would be misleading and fraudulent. So it's important to choose a scale that makes sense and make sure that you label your axis very clearly. You might be wondering if you need expensive software to make these figures. And you don't. There are lots of free resources and online tools available. 2 places where you can get lists of resources that might work for you are Table 3 in the circulation paper. This lists a number of different tools for creating different types of graphs, as well as places where you can find code. And then we recently created a new flip book for R that will show you line by line how to make the types of graphs that are shown in this Q&A. So if you're looking for R code, I would encourage you to check that out. And because it gives line by line control over different options, it will help you to also figure out how to modify your particular graph to work for your data set and optimize it the way you like it. You might be wondering if it matters how you did your statistical analysis, and I'm so glad that you asked because it definitely does. So I'll give a common example to show one of the things that people typically do wrong and then show how you can fix it. And then I'll talk about this a little bit more with another figure. So let's say we have an experimental goal where we want to compare 2 different types of mice. We'll call them a wild type mouse and a knockout mouse. And for my statistical analyses, I have t-tests that were used to compare values for each dependent variable, biomarkers A, B, and C. So in this scenario, a graph that I might often see in a paper is something that looks like this, where I have all 3 of my different biomarkers on the same graph and the comparisons for the wild type mice and then the knockout mice shown in different bar colors. Now, the problem here is that the figure structure is erroneously suggesting that the authors also intended to compare the biomarkers. Because they're on the same graph, I think they're part of the same analysis. And then it's very confusing to me why the authors would use t-tests because it doesn't seem like an appropriate technique. So how do we fix this scenario so that the structure of our figure matches our study design and our statistical analysis? Here is a clear communication strategy. So I simply separate out biomarker A, B, and C into different graphs. And these could be part of the same panel if I wanted to, but putting them on different graphs shows me that I only intended to compare the 2 types of mice, and I did not want to compare the biomarkers to each other. So now the graph structure matches the study design and the analysis strategy. So how do you design figures that match your study design and your statistical analysis? Well, when we're working with simple analyses of small data sets, it's often easiest to show 1 graph per analysis. And you want to remember that that graph should include all groups, time points, or conditions from the analysis as they were entered into the analysis. So let's take a look at what this looks like. So these 2 scenarios are simply versions of what we saw in the last slide. So if I have a comparison between wild type and knockout mice, and I only have 1 outcome variable, biomarker A, then I just have 1 graph. And if I have biomarker A, B, and C, then they would each go in separate panels because I'm repeating the same analysis on different outcome variables. What if I wanted to compare groups with pooled subgroups? So maybe I have male and female mice, and I just want to pool the male and female mice together. I don't want to analyze them separately. So then I'm going to show those pooled subgroups on my graph together in the group as they were in the analysis. And I'm going to use different colors to show them. And that way readers can see, oh yeah, it looks like the male and female mice are similar. It makes sense to pool them. Seems like it fits and like it's a good analysis strategy. What would happen if I did a stratified analysis? So I did one analysis for the female mice and a second analysis for the male mice. Two separate analyses means two separate graphs. One showing the female mice and a second one showing the male mice. And then the last thing I might want to do is test for an interaction. So now I have 4 groups. I have my wild type female and knockout female, and my wild type male and my knockout male. Now all of my groups are in the same analysis, so all 4 go on the same graph. And this is just a reminder, in order to confirm that your analysis is appropriate for the structure of your data and your study design, the reader needs to know exactly what analysis you performed. Very often in the basic biomedical sciences, we'll see a 2-sentence statistics session that reads something like data were analyzed by t-test or ANOVA and statistical significance was determined at p less than 0.05. There are lots of different types of t-tests in ANOVA, and different types work for different study designs. So we need a lot more information than just t-test or ANOVA to know which type of t-test ANOVA was used and whether it was appropriate for the study design. And this paper investigates that phenomenon. It finds that most papers are actually missing the information that we need to see what type of t-test or ANOVA was performed, and it provides a lot more detail about what information you need to report. So if you are using a lot of t-tests or ANOVAs, I would encourage you to look at this paper. Okay, so if you'd like to learn more then about the bar graph issue specifically, or you just want a visual version of this Q&A, there is one on my Twitter account, and I also have slides for teaching available on OSF, and then there's a more extended version of what I presented here in a webinar that I gave for eLife a couple of years ago. I'm going to talk very quickly about a couple of other common visualization problems. The first technique that is helpful is using semi-transparency or gradients to make all of your data points visible. So it was along with the 2018 analysis that we did of peripheral vascular disease journals. And we found that when we looked at dot plots, 46% of them had this problem with overlapping data points, and you couldn't tell how many data points there were, or exactly what the distribution was. With the scatter plots, we saw problems with overlapping data points in 88% of them. And with flow cytometry plots, which are just a very dense type of scatter plot produced by a flow cytometer, we found this problem in 1/4 of papers with flow cytometry plots. So how do we fix these? For dot plots, we've already talked about the solution, semi-transparent jittering, and of semi-transparent data points, also make sure that all of your data points are visible. If you have scatter plots with small sample sizes, then just making your points semi-transparent is often enough for readers to get a sense of how many data points are in particular regions and which regions have the highest data density. If you have a very large number of points that are overlapping, then this semi-transparency won't be enough. Things will get saturated too quickly. And so you may need to use gradients. And you can do these either in black and white by using grid lines, or you can use a blind safe color palette and do a color gradient as shown here. The next thing to do is to replace jet or rainbow color maps with colorblind safe alternatives like Viridis and Cividis. So we'll take a look at this. So rainbow color maps are very common. We see them in scientific visualizations and also in the news media, and everybody likes rainbows. The problem is they're really not that great for visualization. First of all, they're not colorblind safe, but in addition, they also create visual artifacts, even for those of us with normal color vision. And so this is an example of a set of visualizations of the Mona Lisa created by Hyojun Ji. And you can see the normal version that we're used to seeing, a jet color map version, and then a Viridis color map version. And this is colorblind safe and perceptually uniform. What happens with the rainbow color map is that our eyes react much more strongly to the reds and oranges than we do to the blues and greens. And this is a nonlinear effect. And that means that when we look at the gel color map version, we think, oh my God, there's something crazy going on with her chest and with her face. And if I were just to look at the normal version or the Viridis color map version, I would say, okay, they're a bit brighter, but not that much. And these are actually the correct answer. This is our brain overinterpreting what's there. So when we use rainbow color maps, we interpret the data correctly. We think that effects are much stronger than they are due to these visual artifacts. So it's important to really avoid the rainbow color maps, but also for all of your visualizations to choose colorblind accessible colors. When we're talking about color blindness, it's important to remember that the most common form affects up to 8% of women and 0.5% of women, 8% of men and 0.5% of women of Northern European ancestry. So when you think about all of the people that your paper goes through in terms of your co-authors, editors, and reviewers prior to publication, it's quite probable that at least one of those people will be colorblind. And once your paper is published, many of your readers will definitely be colorblind. And if your color palettes aren't appropriate, they will be missing information in your paper that you wanted everyone to have. So you might be thinking, I'm not colorblind. How can I tell whether my figure is colorblind accessible? And the easiest solution is just to use free tools to simulate what a colorblind person would see. Every person is different, so these tools aren't perfect, but they will give you some very clear guidance into helping you avoid common errors. I use a tool called Color Oracle. It's easy to download in about 30 seconds or a minute, and you can quickly click a button to change all of the colors on your screen so that you'll be able to see what a person with 3 different forms of color blindness might see if they were looking at your figure. And running your figure through this type of check is really helpful before you finalize it. Okay, in terms of what color ballots are colorblind accessible, this figure gives you an illustration of some of the issues with common color combinations that we use. So if you use a red-green color combination, it will not be accessible or visible to someone with the most common form of color blindness. If you use a green and blue color palette, it won't be visible to someone with the least common form of color blindness. Whereas the color combinations of cyan magenta and green magenta are equally accessible to all 3 groups. The next point is to include a flowchart to help readers understand your study design and assess the risk of bias. So flowcharts are things that look like this. They give us an overview of the design of the experiment. So I can see the number of animals I started with. They were randomized into 2 different groups and then randomized again into 4 groups. And I can tell how many animals I have at each stage of the experiment and how many were excluded and why they were excluded. And this information about how many were excluded from which groups and why is really important because it helps us assess the risk of bias. And we found in our own meta-research that only about 1/5 of studies had a flowchart. 14% had a study design diagram, which illustrates the design of study, but doesn't imply information about the number of exclusions or reasons for exclusion, which again is essential for estimating the risk of bias. And so we know from this meta-research paper, looking at the effect of attrition in experimental research on cancer or stroke, that biased exclusion of animals greatly increases the likelihood of false positive findings in small studies. And in that paper, they also reported that 7 to 8% of papers were actually excluding animals without any explanation. So we couldn't tell whether that was due to reasons that would cause bias or not. And then 2/3 of papers actually didn't have enough information to determine whether any animals were excluded or not. So again, we have no idea whether these studies have exclusions or whether the reasons might contribute to bias. And then we found similar results in our own meta-research that's unpublished on animal models of preeclampsia. So how do you make flowcharts? Well, if you're doing animal research, then there's a free tool called the Experimental Design Assistant that can help you with designing your study and also creates flowcharts and helps you track exclusion of animals throughout the duration of your experiment. For other types of studies, major guidelines for those studies often have a flowchart template that you can start out with and then modify for your exact study design. So if you're doing observational studies, you might want to check for the stroke guidelines template. With randomized controlled trials, the Consort guidelines offers a template, and for systematic review, the PRISMA guidelines offer a template. And the last point, which hopefully everyone here is familiar with, but avoid 3-dimensional graphs for 2-dimensional data. And the reason for this is the extra dimension doesn't add any information, and it also makes the graph more difficult to read. So if I look at this third dimension, nothing, no information gained. And it's also confusing for readers because readers are never sure whether they should estimate based on the front or based on the back of the bar. And those two things actually give you different values, which is never good. So some people think that this looks better, but it is poor visualization practice. So two-dimensional visualizations with two-dimensional data are simpler, more effective, and more clear in terms of what you want to communicate. Okay, I presented a lot of not just visualization information, but also meta-research information. And there were many people involved in doing those meta-research studies. So I'd like to thank my collaborators at Mayo Clinic and at the University of Belgrade who were instrumental in creating some of those resources. And that includes Vesna Garevic, Stacy Winham, Ethan Heinsohn, and Oscar Garcia Valencia at Mayo Clinic, and Natasha Milik, Marco Savish, and Jelena Milan-Lazovic at the University of Belgrade, as well as my funders. And that's all I have. So I'm happy to welcome questions, comments, or emotional outbursts.